So this is our work and energy video number 6, and I think it's going to be the last one. I threw all the questions that couldn't fit into previous videos into this question. So in the future, if you find any videos in the lessons that you do not understand and need my help or explanation, all you have to do is email me the problem and ask me to record a video with explanation how to solve that question. So here's the first example that we're going to do today. The drawing shows a person who's starting from rest at the top of the cliff, swings down at the end of the rope, releases it, and falls into the water below. There are two paths by which the person can enter the water. Suppose he enters the water at the speed of 13 meters per second via path 1. How high above the water was he? How fast is he moving on path 2 when he releases the rope at the height of 5.2 meters above the water? Ignore the effects of the air resistance. So when he is going with the path 1, he releases the water at the end. He releases the rope at the end, the minimum point, and falls in the water. So the velocity at the lowest point is 13 meters per second. So the velocity right here at the lowest point is 13 meters per second. So that means he has the kinetic energy at the bottom. So he has the kinetic energy at the bottom of path 1. Where does he get his kinetic energy? He gets the kinetic energy from the potential energy. And with conservation of energy, I'm going to say that the potential energy initial plus the kinetic energy initial is equal to the potential energy final plus the kinetic energy final. Because he only has potential energy to start with and doesn't have kinetic energy because he's not moving yet, all I have is mgh. He doesn't have kinetic energy, and equals to, all the way at the bottom, the height is equal to 0, so he doesn't have potential energy final. It is 0, so he has kinetic energy, which is 1/2 mv squared. So because I know the velocity is 13 meters per second, and his mass doesn't really matter, then I can find that the height is equal to 1/2 velocity squared divided by g. So if I plug in the numbers, I have the height is equal to 1/2. Velocity squared is 169, 13 squared, and divided by g, which is 10. So the final answer is equal to, the height equals to 8.45 meters above the ground. So this is where he is located before he hits the water. So from the top, so this height right here is 8.5 meters. So the answer here is 8.45 meters. Now for the second part, since we start again with the potential energy at the top, now initial. So now he goes all the way down to this height, and this height is said to be 5.2 meters above the ground. So I'm gonna call this one is little h now, and this one is big H. So here at this height, he has kinetic energy final, and he has potential energy final. So we will start with what we have at the beginning. He has potential initial energy. He doesn't have kinetic energy, so I'm gonna skip that, writing that one down. And that is equal to, at point 2, he has potential energy final plus the kinetic energy final. So here I have mgh, and I just found what that h is equal to. I already know that number. Equals to mgh, and they give you what that height is equal to, plus 1/2 mv squared, and this is at point 2, velocity at point 2. Now, every single one of these has terms m, so I'm going to cancel m from every single term. And I'm solving for velocity at point B. So the velocity at point B is equal to 2g, and then I have h minus h. It's 2gh formula, the square root of 2ad. And I have the square root of 2, 10, and h is 845, minus the new height is 5.2. So the velocity is equal to 8.06 meters per second. I think this is a somewhat challenging question for some students, so let's do it here in the video. A particle of mass 0.5 kilogram is shot from point P as shown. The particle has an initial velocity vi, so that's initial velocity, with a horizontal component of 30 meters per second. So I know the horizontal component of the particle when it's shot is 30 meters per second. So that horizontal component does not change. It will stay all the way through, all the way till the end. I'm going to say this is like right before it hits the ground, so it stays the same 30 meters per second. The particle rises to a maximum height of 45 meters above point P. Using the laws of conservation of energy, determine the vertical component of initial velocity, the work done by the gravitational force on the particle during this its motion between point P and B, and then the horizontal and vertical components of the velocity vector when the particle reaches point B. So at first we're going to figure out the horizontal component of of the initial velocity. So we're trying to figure out this vertical velocity. And because I know that the height is 45, I can use the vertical velocity and I know acceleration. So I know the final velocity formula, because I know distance and acceleration, is equal to the square root of 2 times acceleration, in our case is g, times the distance, that's the height of 45 meters, plus the initial velocity squared, so that's vy initial squared. And vy initial is the one that I'm looking for. So if I square both sides, I have v final squared, and I'm going to subtract 2gh, and is equal to initial velocity squared. So if I take the square root with both sides, the square goes away, and now I'm going to plug in the numbers. So I have the square root, final velocity is 0, minus 2, acceleration is negative 10 because it's losing its speed, and the height is 45. So it looks like that is going to be 30 meters per second. And some of you knew it was 30 meters per second from the practice questions that we already done in the classroom or here through the videos. So we have 30 meters per second. And because we know horizontal velocity and we know vertical velocity, I can figure out what the actual initial velocity was. I'm going to use Pythagorean theorem from that triangle. I have this equals to 30 squared vertical velocity plus horizontal velocity is also 30 meters per second, because that is what they give you in the statement. So what I have is 2 times the 30 squared, or the initial velocity is equal to the square root of 2 times 30 squared. So initial velocity is equal to 42.43 meters per second. And they don't ask you to find this velocity. All they ask you to find is the vertical component. So your vertical component is going to be 30 meters per second. And then for the next part, what work is done by the gravitational force on the particle during its motion between point B and P and B. So between point P and B, the potential energy at P is the potential energy at P is equal to m, g, and h, where h is 60 meters. So the mass is 0.5 G is 10, and H is 60. So that gives me 300 joules. That is the potential energy, 300 joules. And I'm losing all that energy. I know that the work by the gravity is going to be equal to the change of the potential gravitational energy between P and B. So the final potential energy at B is 0 and initial is 300. So the work is also equal to 300 joules. And then the last part, the horizontal and vertical components of the velocity vector by the time it hits the point B. So the horizontal velocity does not change. Horizontal is still 30 meters per second because that's what they give you, 30 meters per second. What I need to find out is what the vertical velocity is equal to. And the vertical velocity at point B, or the final velocity, is equal to the square root of 2 acceleration. And the height is 45 plus 60 because it falls down from the height of 45 and 60 meters together. So, and that velocity is equal to 46 meters per second. So that is the vertical velocity. But if I want to find the actual velocity at which it hits the ground, so I'm going to call V final. So if I wanted to find that final velocity, I can use Pythagorean theorem again. It is the horizontal component, which is 30 meters per second, plus the vertical component, which is 46 meters per second squared. And that will give me 54.9 meters per second. I can round it to 55 meters per second. So the actual velocity at point B is the one that I marked in red in the picture. That velocity is 55 meters per second, but the horizontal and vertical component are 30 and 46. I also want to cover power concept with you, and the power is going to be equal to how much work is done per time. So let's say you have 2 people and you leave some job for them, and one person can lift 50 buckets in one day, and the other one can only lift 20 buckets in a day. So the person who can do more work over the same amount of time is more powerful. So the power is how much work done per time. So right here in the formula, you see the power is equal to how much work done per time. And I'm going to derive the second formula. So on AP exam, you're only going to be given this formula, nothing else. But often the questions related to more than that. So the power is equal to work over time. But the work is force times the distance, cosine theta. But if we assume that the work is done with the angle horizontal to the surface, if it is the distance of horizontal as well. So that is going to be 1 over the time. And distance over time is the velocity. So I have the force is equal to force times velocity is also power. And the power is measured in watts. So it's the same as joules per second, energy per second, how much work done per second. But another word for it is watts. Let's look at one of the examples, number 27 in our lesson. So in number 27, they say 15.5 kilogram block is pulled across the flat deck at the constant speed of 3 meters per second with a rope. The rope is horizontal to the deck. The coefficient of friction is 0.33. How much power does it take to do this, to pull the block? Because they say that it is pulled at the constant speed, that means if I have a block and I am applying the force, applied force, and then there is also friction force, that means the friction force is equal to the applied force, because your acceleration is equal to 0. So when they say how much work is done, how much power is required to do this work, I'm going to say the power is equal to the work over the time, the force times the distance that will be pulled over the time. And distance over time is again the velocity. So I'm going to use that formula that I just explained to you. So it's going to be the force times the velocity. And the force is equal to the friction force because these two forces cancel each other. So I could write as this force times the velocity. It doesn't matter which one I choose. So the power is equal to, the friction force is mu times n, but because your forces are mg and normal cancel each other, they're equal to each other. So they're the normal force is equal to mg, and then it times the velocity. So now I'm going to plug in the numbers, and I have 0.33. The mass is 15.5. G is 10. And the velocity is 3. So I get the power is equal to 153.3 watts. The questions with power in these sections, they're pretty similar to each other. You just have to find the work and divide by time to find the power. So I'm going to skip other questions. You can practice them online in our PDF files and lessons. So here's one question that I want to look at as well. So sometimes you see the graph on AP exam and you have to figure out how to solve those type of questions. So suppose a 2 kilogram model car is initially at rest at x equals to 0, and a force is the net force acting on it. Use the work energy theorem to find the speed of the car at 3 meters and then 4 meters and then 7 meters. So if you look at this area, the area is usually base times the height, and your base is distance and the height is force. So the area underneath this graph represents work. So if I want to find the work done on the object, I will say the work is equal to, but I have to break it into two different areas. At first this one, and then the second one. So there's 1 and 2. And the work done on the first one is the area of the triangle, which is 1/2. The base is 2, and the height is 2. And the work of the second one is the base times the height. So I get 2 plus 2. The work is 4 joules. So if the object started from rest, then this much work was put into the car. That means that is equal to the change of the kinetic energy of that car. So the change of the kinetic energy is the final minus initial, but the initial velocity was 0 because it started from rest. So this 4 joules is actually the final energy. So the final kinetic energy of the car is equal to 4 joules and equals to 1/2 the mass and the velocity at 3 meters and then squared. So if I plug this in, I have 4 is equal to 1/2. The mass is 2, and then velocity squared. So the velocity at 3 meters is equal to 2 meters per second. So that was my A. For B, I need to find the velocity at 4 meters. There is no work done, no force acting, and no work done on the car. So that means there is no change of the kinetic energy. So the velocity at B, so for 1 meter, the force was not acting on the car, so the kinetic energy of the car will not change. So the velocity at 4 is still 2 meters per second. Then there is going to be negative work done on the car, and the negative work, that means it will be losing velocity. So how much work? Maybe that was friction because no force was acting. Maybe the car started slowing down. So I'm going to figure out how much work was done. So the work for the last part is equal to, you could use it as the area of the triangle, but I'm going to use a different technique right now. I'm going to use average force times the distance, and because it starts with the force of 0 and ends up with the force of -1, average force is 1/2 and the base is 2. So that is 1 joule of energy, and that is equal to, and it's negative, right? It's negative. And if you look at this triangle, the area of that triangle is 1. So I have -1 joules, and that is equal to 1/2 mv final squared. And I'm not going to plug in the negative number, but that will tell me how much velocity is lost because the negative work is done. So I will know exactly velocity at 7 meters. Or actually, this one is still at 6, and then that one is 7. So then I have the mass is 2, so the velocity that is lost is equal to 1 meter per second because of the negative work that is done. So -1 meter per second. So the velocity at 6 is actually equal to 1 meter per second because I used to have 2 meters per second, and now I'm losing 1 meter per second, so my velocity at 6 is 1 meter per second. But then no force is acting, so the force is acted here, the force acted here, acted over here, and did not act over here, then acted in the to slow it down, and then does not act anything over there, so it will not change the velocity that you already have. So the velocity at 7 is the same as velocity at 6, 1 meter per second. So here is one more question, and they already kind of pre-solved for you. So the blue part of the force over the distance is cancelled. So you have the blue area, let's do it green. This green area is positive and then negative. So maybe your car accelerated and now it's slowed down by the same much, so the net work is equal to 0. Then they have this area, so you have negative work done and then you have positive work done, so those two also cancel. So what's left here is this purple area and the blue area. So I only have to calculate how much work is done over these two areas, the last two, because the other ones cancel each other. So if I calculate the work done in the pink part, so let me choose, I'm going to choose red for this part. So the work done here is equal to the area, so the force is 10 newtons, and the distance is 2 meters, so that gives me 20 joules. And the work done over the last part, so I did the red one, and now I'm doing the blue one. The work done on the last part is average force, so the final is 0 and the initial is, so it starts at 10 and then goes back to 0. So the average is 5 and the distance is 2 meters. So that is 10 joules. So the net work done on the object is 30 joules. And this energy is the one that you put into accelerating an object. So that is by how much your kinetic energy has changed. And they tell you that final velocity of the block, find the final velocity of the block, 2 kilogram block, if initial velocity was 2 meters per second. So if the change of the kinetic energy is equal to 30 joules, that means the final squared minus initial squared is equal to 30 joules. So if I want to find the final velocity, I'm going to plug in the numbers for initial velocity. So let's plug them in. I have 30. Let's times them all by 2 so we don't have fractions. So if I times every term by 2, I have 60. And then I have mass, which is 2. Final velocity that I'm looking for, minus, I times it by 2 so fraction goes away. The mass is 2 and initial velocity is 2 meters per second. So if I divide them all by 2 now, because I can, so I have 34 is equal to v final squared. So that gives me the final velocity of the object is equal to the square root of 34, which is 5.83 meters per second. Here's one last question for this video. A spring in its unstretched position is mounted to the wall at the height of 1.8 meters above the ground. After the spring is compressed by 20 centimeters, it releases the ball of mass 0.1 kilogram, which is landing 5 meters away from the wall. Calculate the spring constant. So I know that the distance is going to be 5 meters. So the distance is 5 meters. And I know that the height is 1.8 meters. So when the ball is released, it has initial horizontal velocity, but it doesn't have vertical velocity. Vertical velocity appears as it starts falling down. So initial vertical velocity is 0, but I can calculate the final vertical velocity because I know acceleration due to gravity and I know the distance. So I'm going to say the final vertical velocity is equal to the square root of 2 acceleration, and the distance is 1.8. So I get 6 meters per second as it hits the ground. If it hits the ground at 6 meters per second, then the time it takes to fall on the ground is the change of the vertical velocity over acceleration, and that is 6 minus vertical initial is 0 divided by 10. So in 0.6 seconds the ball is going to hit the ground, and I need to calculate I can calculate the initial velocity now. So because it landed 5 meters away, distance 5 meters away, I can find initial horizontal velocity, and that velocity doesn't change. So horizontal velocity stays the same. So I can say that initial horizontal velocity is the distance traveled over the time. So that is 5 meters over 0.6 seconds. And I get 833 meters per second. Where did the ball take this horizontal velocity? This is actually the kinetic energy that the ball has. Where did it take kinetic energy from? It took from the potential energy of the spring. So I can say the potential energy of the spring, which is 1/2 kx squared, is equal to the kinetic energy of the ball after it was released. So that's 1/2 mv squared. So 1/2 and 1/2, and that is the kinetic energy of initial velocity. So 1/2 and 1/2 is cancelled. X is given to 20 centimeters, so I have k times 0.2 squared is equal to, the mass is given of 0.1 kilogram, and the velocity is 833 squared. So my k is equal to 173.47 newtons per meter. This was our 6th video on power, energy, work, and the next video most likely is going to be on momentum. And unless you email me and ask me that you found some questions that we have online or in the book that you don't understand how to do, I'm gonna stop here for work and energy. And if I do other videos on work and energy, I will post their links in the description of this video. And that is it. See you in the next video where we have momentum.